continuing on with the magazine theme that I've had for the last two sections with life and with time. This is Rolling Stone. This is geology after all, right? So we're going to look at today, episode 3, we're going to look at relative time and how geologists do that sort of activity. And we're going to actually celebrate a guy named James Hutton. James Hutton is what I regard as a real rock star. He's regarded as the father of geology as well. But James Hutton gave us some very important concepts. He gave us the concept of a angular unconformity, but he also gave us the idea of deep time. So deep time is what we look at in geology. And so what is deep time? What is relative time? What is absolute time? We'll get to that later. What are unconformities? And there are some other mysterious features that we find in the rocks, recorded in the rocks, sedimentary rocks mostly. So we're going to start this by saying, okay, first of all, thanks for taking part in the pre-course assessment. Those of you who did, and most of you did, so I was very happy to see that, and you'll find 5 points of extra credit in your grade book now too, so that's good. Also, I'm going to try to get these things cranked out in a timely manner, but it takes about 10 hours to do. Like the last one, I think episode 2 took about 10 hours to do all of the recording, the processing, and everything else, and to get it uploaded. So it takes a while to render it and so forth. So I do other things in the meantime, right? While it's working on things on a computer, but at the same time, it takes a while to put these things together. So please be patient with me, I guess I would say. So there, and we already broached the subject of like Buddhism with Mahabodhi tree in India, but and I told you about the 4 noble truths that the Buddha, or at least 3 of the 4 noble truths that the Buddha given us. But just studying a little bit about him and about his noble truths, it made me realize that we also have some noble truths in geology, and I actually wrote these down several years ago, and then somebody wrote it in a book about me. The book is not about me, but the book is about Missouri geology, and it was a very complimentary sort of thing that somebody had recognized that I'd posted these on my website. So I'm going to post them for you. And these are what I think are the 4 noble truths of geology. And so the Earth is very old. And we'll talk about deep time, right? Earth is dynamic. We have a very active Earth with subduction and new material being added at spreading centers and so forth. So plate tectonics is that activity. Number 3, life evolved on Earth. We don't know exactly where life came from, but we're pretty sure we know that it evolves on Earth. So that's a good thing. And then lastly, humans exist in a perilous geologic environment. And we can take some lessons from the past as well. That's one of the reasons why this course is offered, so that we can learn and not have the same things happen to us that happened to the non-avian dinosaurs. So that would be a good thing. Okay, so most people think that geology is looking at rocks, and it is actually partially. Geology is really the study of the processes of the Earth and the other planetary bodies. We claim all of the rocky planets now for our study, and even some of the icy planets out in the far reaches of the solar system. And when we can get there, when we finally get there, even the exoplanets that may be in nearby stars. So that's our domain, I guess I could say, in the science of geology. That's what most people think is the process sort of thing and the kind of results, the rocks that you get out of that. Well, that's partly true. Geology also, and a lot of people really don't understand this, but it is the study of time. And so the study of time is really important in geology. And that's the aspect that we're going to deal with here in Life of the Past. So you probably know this already, but there are 3 rock types, right? Igneous, sedimentary, and metamorphic rocks. We're not going to talk about rocks in this class, but we do talk about the sedimentary succession. And so because of that, you'll hear some terms like limestone, sandstone, shales, things like that. And I'm not going to expect you to know a whole lot about it, okay? So don't worry about that. Those are things, if you want to learn more about the rocks, you can take Geology 110, and actually the companion course to that, I think it's going to be called, well, I'm not sure, I think it's 120. It's going to be the lab that's going to be separated then from Geology 110. The reason why we talk about sedimentary rocks is because we have to talk about the concepts by which we put together a relative time scale in the geologic past. So we go back into the 16th, 17th, 18th centuries, 18th, 19th, and even into the 20th century. Many new concepts were developed, but we're going to start way back with a gentleman named Nicholas Steno. At least that's what we call him today. He gave us several concepts in geology, including original horizontality, lateral continuity, and superposition. We're going to talk about James Hutton some more, the father of modern geology. And he gave us the angular unconformity, and he gave us the concept of deep time, that it takes a long time. The Earth cannot be a very short-lived sort of planet, And then Charles Lyell was another pretty important geologist, and he gave us the idea of cross-cutting relationships. Actually, some of these other earlier geologists came up with the same concept, but in fact, he's the guy who actually wrote it down for the first time. And then we're going to talk a little bit about the geologic time scale. And then in the next episode, in episode 4, we're going to talk about absolute time and relative in the connection to relative age dating. And then in episode 5, we're going to talk about the structure of the Earth and plate tectonics, just to give you a background, because we have to move the plates on the surface of the Earth around a little bit, and it gives us a different biogeography through time, and so animals migrate. And that's a little bit of what's in this book that has been assigned to other lands. And so in other lands, I've been listening to the first 4 chapters so far in this, and he talks about Beringia, which is in between North America and Asia. So it all has to do a little bit, anyway, with plate tectonics and climate change, actually, too. So pretty important topics for our modern world. Okay, so let's get going on this. This image right here you see is the Platonic Academy that was developed by the Medici family in Florence. And so one of the guys who put together this consortium of academics and researchers, he recognized talent in some of the earliest scientists, and that would have been Lorenzo Medici. And so Lorenzo and his brother were the rulers of Florence at the time, and from a very rich and wealthy family, and they established an academy here. So the original Platonic Academy, of course, was founded by Plato, who was a student of Aristotle. And so the very earliest Western philosophies were developed in Greece. They were adopted in Roman culture and then developed in the Italian states at that time. And so this is the Florence is one of those sort of principalities, I guess you could call it, actually a duchy. And Nicholas Steno was kind of hired on for this. Nicholas Steno was a famous anatomist, and there's a book written about him. If you're really interested in Steno, the book is called The Seashell on the Mountaintop. And it was Steno who also gave us this idea or the concept that fossils they're not just part of the rocks, they actually are the remains of once living creatures that have since died. And it goes back to a time period when he studied some of the glossoptery, they call them. They were actually shark teeth. And people had thought, well, these are weird looking rocks that must have been created by lightning or something, right? And it's like, no. From his anatomy, he dissected a shark and said, look, these teeth are almost the same that you get in Malta on these features that are called glossoptery. Anyway, Nicholas Steno, he gave us 3 major concepts, and that's his publication, Dos Solito. And so it was really important contributions that he gave us. So let's talk about original horizontality. On the left-hand side, that is a walkway that goes through a state park in upstate New York, and it is a place called Watkins Glen. And so Watkins Glen is this very steep-sided valley that this area was glaciated, and so it cut a lake off to the east of Watkins Glen, and so this river cut down very, very rapidly to meet where that glacial lake was deposited. And so when that river or this stream cut through, it etched out or ground out this beautiful, beautiful valley. And today, of course, it's a state park, so you can walk up and down Watkins Glen on these trails like you see on the left-hand side here. And there's water everywhere, right? So upstate New York, a very wet state. So, but if you look at the rocks, you can see that those things are actually horizontally bedded. And that's one of the principal things that Steno gave us. Nobody had written it down before, and so he says, rocks were originally horizontal when they were deposited, and they would go on laterally as far as they could go until they either met a barrier or they petered out, right? So the sediments would just like die off. There's no more sediment to give. You can't extend that sheet of sedimentary rock then. So first they become sediments, and then they get buried, and then they become sedimentary rocks. On the right-hand side, this is another place where I had the opportunity to visit, and it's an area that's actually part of the Appalachian Mountain Belt, if you will, but it's in Sweden. Okay, they're ancient rocks here. They're Cambrian age, in fact. So we're going to talk about the ages later. But this is on a little island in the fifth largest lake of Sweden. It's called Frösön, and it's a province called Jämtland. And the Jämtland here has these sort of thrust faults like this. And you can see where the bedding is in these rocks. It's actually relatively horizontal, but they've been bent and twisted. And so that's actually a thrust fault right at the bottom of that feature. It's, for a geologist, that's a textbook feature right there. It's like, wow, look at that thrust fault. But the layers themselves were originally horizontal. And so they, in order to be preserved, like, in other words, those rocks were not deposited in the appearance that they have today. Okay, so when North America collided with the other continents to form the supercontinent Pangaea, that's when this thrust faulting occurred, and it bent those rocks. And so this is part of a mountain range that, together with the Appalachian Mountains in North America, became known as the Caledonides. And so the Caledonides stretch all the way from Sweden and Norway to northern Scotland to Newfoundland, and then over to all the way down into Georgia. And so it's really an area in Alabama. So really a fascinating story about how the continents move around and they cause deformation in rocks like this. But the rocks originally were horizontal when they were deposited. And they've been faulted and fractured there on the right-hand side. So original horizontality. If we look at the next page here, this is the rocks that are in the Timber Range in California. You can see that they're actually dipping now. So they weren't originally dipping that way, but these are Miocene age rocks, so relatively recent age rocks, less than 15 million, 20 million years ago. And that's in California. So California is very tectonically active, and it's a place where, in fact, these rocks have been tilted up in order to place them in that sort of orientation. In the bottom down here, that's in Texas. That's in the Marathon Mountains, and those are really, really deep water rocks there that consist of sediment gravity flows. They were originally horizontal when they flooded out of a submarine canyon, and then they were deposited in a thick succession. And then, back when Pangaea was forming, the Marathon Mountains were part of that chain that goes from Alabama, goes through southern Arkansas in the Ouachita Mountains, goes through central Texas in an area called like the Llano Uplift, and here we are in the Marathon Mountains out in West Texas. I think that's about as far as you can trace that sort of mountain range, but this would have been part of that same collisional mountain range that formed when the Appalachian Mountains formed about 300 million years ago. So the rocks could be much, much older, right, than what the actual deformation is. The rocks that you saw in Sweden were Cambrian in age, which is about 500 million years ago, but the deformation occurred at 300 million years ago. Originally, all of these rocks would have been horizontal. The ones in Texas here put into a vertical position. If we go on to the next page, you can see a picture of the Grand Canyon. This is one of the favorite places for geologists, I have to say. Sedimentary rock succession here covers up some ancient rocks down at the very base of the canyon in a place called the Inner Gorge. The Inner Gorge has some granites, and has the Vishnu schist, I think, is the oldest rock there. And then you get the Zoroaster granite that intrudes into it. And then there's some sedimentary rocks that were deposited and then tilted afterwards. And so there's some Precambrian sedimentary rocks at the bottom of the canyon as well. And then at the base, near the base of some of these cliffs, you actually see in this picture here, these were deposited during a time period called the Paleozoic. So the Paleozoic is an ancient lifetime. And so that's, in fact, the canyon itself, where we have the Paleozoic rocks, it records all the way from the Cambrian, which is about 540 million years. Here, maybe a little bit younger than that, about 525 million years, to the very top up here, and that's in the Kaibab Formation at the very top. It's the Kaibab limestone. You can see it just actually over here on the upper left-hand side. Those are the rocks exposed at the very top of the canyon. Well, they're like sheets of paper almost, right? So the Cambrian down low and the Kaibab up high here. And the Kaibab's about 220 million years, I think, something like that. So maybe, no, it's 250 at least. So it's got to be maybe closer to 280 million years old. So from 530 or 540 all the way up to 280 million years are recorded in these Paleozoic rock successions here. Now, what's interesting here? Okay, the lateral continuity concept that Steno gave us, he says that these things will go on forever until they either hit a barrier or they peter out in some way. In this image, you can actually see the Kaibab limestone. You can trace it all the way across that canyon. So the canyon itself has to be much, much younger than what the rocks are that make up the walls of the canyon, right? So you have to deposit the rocks first and then cut them with a river and have erosion make this sort of gouge through the earth here. And it's one of the largest gouges in certainly in North America, maybe the world. There are some deep canyons in other places around the world as well. So the Kaibab limestone originally stretched all the way across this landscape, and so that's the lateral continuity that he was talking about. Superposition. This one's pretty easy, and you would say, is that really something? He's like, well, it is, because we have to deal with some exceptions in geology as well. And normally, when you have a succession of rocks, they're layers after layer after layer. They're deposited in a series of events, right, and over a length of time. And so over here on the left-hand side, you can actually see Mesa Verde in Colorado, and that's Cretaceous in age. You can see shales at the very bottom. That forms a slope. And at the very top, there's a sandstone there. Eventually that's going to be a place where on the south side of this exposure here, there are a whole series of canyons there as well that cut into this mesa. And it is fascinating because Native Americans found the caves that were on the overhangs that were there, and they built entire cities in many of these canyons. So very important culturally, but it's all because of the layering of the rocks. Well, I had to take a little hiatus there, but I'm back at it now. It's another day. And superposition is this idea that rocks are stacked on one another, one on top of another. It indicates that the oldest rocks are at the bottom and the youngest rocks are at the top. So it's a kind of a common sense principle in geology, but at the same time, it's one of these things that had to be written down by Steno. Steno's the guy who gave us this idea of superposition. I already mentioned on the left-hand side, and the lower left-hand side, you can see Mesa Verde over here. There's a little erosional remnant you can see on the right-hand side here, which is pretty cool too. That's that same sandstone, in fact, part of the Mesa Verde group. I think it's called the Farron Sandstone here, and it's surrounded by slopes of shale below it there, so a little bit of a mesa, if you will, here as well, and surrounded by snow, obviously, too. So if superposition is this idea that always we have older rocks down low and younger rocks that continuously, successively overlie them, it gives us some indication of the relative age. And that's what we're getting at here, the relative age dating, right? And so it all works great until in the early 1900s, somebody discovered and first published on a concept called thrust faults. Thrust faults are unique, in fact, in geology, where older rocks can actually be placed on top of younger rocks, and that's through processes of deformation, structural geology. And so thrust faults are where rocks get pushed over the top of other rocks. And the first ones that were described, of course, were in the Alps and also in Scotland. And there's a lot of them in the Appalachian Mountains and some out west, obviously, too. And so here is an example of what these things look like when you see a thrust fault. So on this next slide here. So if I can get it to show here for me, there we go. That's the Hart Mountain thrust. And so the Hart Mountain thrust is in Wyoming, close to the town of Cody. And it places some Precambrian rocks on top of Cretaceous rocks here. Now what you see down here in the lower left-hand side, you can see the same sort of view from a geologist's interpretation. And so this actually shows you the layers one after another, and then that thrust fault that kind of ramps up over the top of these other rocks. That happens in situations where you get a mass that slides down across, and that's, I think, the interpretation for Heart Mountain Slide, in fact. So it places 340, well, it's not Precambrian rock in this situation. That's at the Lewis Thrust, and that's in Glacier National Park. Here at the Heart Mountain Thrust, it pushes Mississippian age limestones over the top of an Eocene shale. Okay, so it's an ancient landslide essentially here. Sorry, I had the wrong one there. It was a Lewis thrust I was thinking of earlier. But in fact, a thrust fault will then place older rocks on top of younger rocks. And so we always look to what kind of context these rocks are in, right? And so in this case, we have a thrust relationship or a structural relationship as opposed to a stratigraphic relationship between the rocks below and above. Okay, if we continue on, we're looking at James Hutton here. This is an old farm here. It's called Slee Houses. It's in Berwickshire in Scotland, and so it's in the lowlands of Scotland. He had a farm there. James Hutton trained to be a physician. He went on. He didn't like the sight of blood apparently, and so he went on to become a gentleman farmer after that. And all the time, he was just a natural scientist. He was one of these guys who got into nature and tried to understand what was going on in nature. And so at Slee Houses, he began to farm. And he noticed that there were small drainages that cut across his land that were carrying silt, from his land into that little stream that was nearby, and that would take it into a river, and that river would then take that sediment into the ocean nearby, right? So it was the North Sea that he was looking at there. In his house also, if he looked across not far away, he would see Roman ruins. And so the Romans were in southern Scotland, and he said, wow, those ruins have really been weathered. And then he looked nearby, and there's a medieval castle over here, and that medieval castle also had been weathered by the ravages of storms and rain and things like that, the ice and the cold and the wind. And so he noticed it's like, well, the Roman ruins are much more deeply weathered than the medieval ruins because they're 500-800 years older. And so he put together this idea. It's like, well, erosion and weathering wear down sedimentary rocks. They'll wear down any rocks, right? So anything you build that's a masonry sort of, and you can see the rock wall in front of his house here. It's the idea that the elements, the atmosphere, in fact, is good enough to like break down things through time. We know that things go to wreck and ruin. So with that in mind, Hutton said that, okay, if we have rocks that can get weathered, they can get eroded, that is carried away and transported out to a depositional setting, they get deposited, and those sediments then can become sedimentary rocks. That was a revolution right there. And then he said, I'm going to start looking at these rocks around me. And so he recognized the old red sandstone. He recognized some other rocks in this area. And he put his ideas together, and he built, this sort of model for how he thinks the Earth worked. He was also a person who was convinced that most sediments actually come from igneous rocks originally. So he was what we would call today a Plutonist. And so these sediments were actually derived from igneous rocks originally, and that those igneous rocks would become sedimentary rocks. And so that's what Plutonists believed at that time. And so he put it all together for the Fellows of the Royal Society. He was giving a talk for the Royal Society, and before he did that talk, actually, he rounded up some friends of his, John Playfair and a guy named James Hall, and they said, well, let's go take a boat ride, because I've seen this unusual feature at a place called Jedburgh, and it looks like the sedimentary rocks are all disrupted there. They're actually vertical, and let's go see if we can find this along the Berwickshire coast. And so they rented a boat, and they had a crew sail them along the coastline of southeastern Scotland. And so as they sailed along that coastline, they were looking at the rocks very carefully as they would sail by. When they did that, they actually saw the old red sandstone, and then they also saw the old red conglomerate that was below that. And as they're sailing along, those rocks began to kind of peter out as they went farther and farther south, and they recognized, oh, look over there. There's some older rocks that are not in the same sort of orientation. They were actually vertical as they went by. And so eventually they came to a place called Sicker Point. And at Sicker Point, they discovered something really, really unique. And it was the first time anybody had ever documented this. And so they pulled the boat ashore here, and they saw this feature. That is the Sicker Point angular unconformity. And this, my wife Nancy, they're pointing to the unconformity. There's a little tiny basal gravel or basal conglomerate at the base of the old red sandstone there. But below that, you can see the vertical Silurian Gala group. And so the Gala group is a greywacke. Now, you know what a greywacke is, perhaps, but maybe not. It's a dirty sandstone. It's essentially a sandstone that was deposited in deep water. And then at some point, those rocks became deformed, and they were tilted and actually emplaced vertically. And then you had to erode across the top of those vertically emplaced rocks. And so after that, the old red sandstone was deposited and then eventually tilted a little bit more. And so that's an angular unconformity. We say that it's rocks that show angular discordance between the rocks above and the rocks below. Notice both of them are sedimentary rocks. That is one type of unconformity that we refer to as an angular unconformity. It's one of the first ones ever described, in fact. There's roughly about 50 million years missing there. And so what happened between the Silurian and the Devonian here was an event that marks a collision. It's a collision that actually saw the first beginning of an island arc that collided with North America, in fact. So this was actually part of North America at that time. And when it collided, it actually tilted the rocks below, and then the rocks above became part of the continental sedimentation that was being deposited afterwards. So that was an angular conformity here. And what Hutton did next, he sat down, he sketched it, of course, and after he sketched it, he realized it's like, oh my gosh, geologic time must be absolutely immense in duration. And so he said that there's no evidence of a beginning and no vestige of an end in geologic time. So he was a person who thought that the Earth was infinite in its dimensions, essentially through time. And it's like today we know that's not true. We know that the Earth began about 4.5 billion years ago, and we know that at someday, maybe in another 5 billion years, the Earth is going to disappear, maybe as little as 3 billion years, but it doesn't matter. That's way beyond the scope of what human beings can actually even imagine, kind of. We have an Earth that is exceptionally old. There are the four the four noble truths of geology. Earth is very old, and this bears it out, actually. And so they pondered that. And it was Hutton that came up with this idea also that the processes that work in the present day, like around his farm, the slee houses, worked in the ancient past as well. So if there's erosion in the modern world, there's erosion in the ancient world as well. And this is a result of that ancient erosion between the Silurian and the Devonian. It's like, so these things happen, okay? So that's an angular unconformity. There are other types of unconformities as well. This is called a nonconformity. This is where you have igneous rocks that have been uplifted and then eroded, kind of beveled off, and then sedimentary rocks were laid over the top. These too have been tilted somewhat later in their orientation here. But at this surface right here, this is again out in western Wyoming and northwestern Wyoming near the town of Cody. And that's the Cambrian Flathead Sandstone, which is about 540 million years old, over about a 1.7 billion year old Precambrian granite. So that granite was in place at some time, had been uplifted, eroded, and then the sedimentary rocks were laid down over the top. That's called a nonconformity. So you know about angular conformities, you know about nonconformities. And in fact, let's look at this one closely here. Here you can actually see that Precambrian basement. We call it basement because it's the lowest part of the Earth, at least the Earth's crust. And so above that, then we get this Cambrian sandstone. That's the Flathead sandstone. We we know that these sort of features represent missing time then. Sometimes they also represent uplift. In an angular unconformity, it represents uplift. In a nonconformity, it represents uplift. And sometimes in these other features that are known as disconformities, they also represent some sort of uplift and weathering as well. Now, this is in coastal California here, and here you can see some Cretaceous age rocks, and those are about 100 million years old or so, overlain by Oligocene rocks, and those Oligocene rocks are probably around 70 million, no, they'll be 50 million, probably about 40 million years old, okay? So roughly, and there's about 20 million years missing, okay? So yeah, so if I do the math here, that's like the Cretaceous at its very youngest, that's the age of the dinosaur extinction, right? That's at 66 and a half, so probably a little bit older than that. But there's about 20 million years missing at that unconformity. And so you can see, again, the irregular shape of this, and so that's called a disconformity. There's certainly evidence for erosion there, but it's sedimentary rocks over sedimentary rocks without angular discordance. And so that's a disconformity. Three main types of unconformities right there: angular unconformity, nonconformity, and a disconformity. And so those three things tell us a little bit about the packages of rock that were deposited in geologic time. If we look at something called cross-cutting relations, this is another one of these key geologic principles that we study in geology. Here you can see actually a fault that cuts some sedimentary rocks. This is up in the northwest corner of Colorado, and this is near Flaming Gorge, I think they call it. And on the right-hand side, that's a Sheep Creek Canyon geologic area. So these two areas are really close together here. The fault cuts the sedimentary rock, and so when that happens, that's been offset. That's a fault is a fracture with offset, and so the offset actually puts a vertical component to the rocks, in this case on the right-hand side, and so that fault cuts those rocks. So the fault has to be younger than the rocks that it cuts, right? The image on the right-hand side, there's Mississippian age rocks right up against Precambrian rocks there, Precambrian, mostly sedimentary rocks, I think, here, but that's the Uinta mountain group here. And so those are in fault contact as well, but it's kind of the Mississippian age rocks were kind of lifted up, if you will, on the right-hand side. Well, they were dragged down, I guess you could say. All of these rocks were uplifted on the left-hand side, but they were dragged down on the right-hand side and then folded as well. So, and their vertical orientation there. And so they didn't get laid down that way because of original horizontality. But in fact, the cross-cutting relationship here is that it broke the rocks and places those in fault contact with one another. The fault itself has to be younger than both of those rocks then. So, cross-cutting relationships. As it turns out, when I first made the first slide here, you remember Charles Lyell, right? So Charles Lyell is the guy who first published on this. Steno is probably the first person who actually noted that rocks have cross-cutting relationships, but Lyell was the first person to make a geologic textbook, and so that's his contribution to this presentation. Next, we go to another concept, and that's geologic mapping. In other words, when we map out the surfaces of these rocks, and geographically you can actually determine how far those rocks go. And so here you can see on the left-hand side is all the way from an area called the Cotswolds all the way across Wales here. And on the right-hand side is the original geologic map that was made. And so that was published in 1815 by a guy named William Smith. William Smith was a British, they called them jobbing ditchers. Okay, so there's many wetlands across Britain, and because they wanted to drain those wetlands and turn them into useful farmland or grazing for in pastures and so forth, he would cut ditches across this landscape. And when he did that, he found that underneath of the soil and so forth, in the bedrock, he would find fossils. And when he found these fossils, he says, oh, well, these are the same kind of fossils that I saw at this other place. So he collected these fossils and described them in great detail. And so he made this first geologic map through his notes just by working across the country. He was a traveling engineer, essentially. We would call him an engineer today. And he made a geologic map. And in that geologic map, in fact, He submitted it for publication, and of course it was stolen immediately by the Fellows of the Royal Society in London. And but eventually they came around. They actually awarded him the Wollaston Medal for his accomplishments as making the first geologic map of Britain and Wales and southern Scotland. So you can map geologic rocks. In other words, you can map the geology of an area, and it's very important to know what those resources are there. It became the foundation for much of what the energy industry uses today, but it's also the background for what we do in geology and in all aspects of geology. Geologic mapping is one of the most important endeavors that we do. And in fact, I sit on one of the committees for the state, actually, and we look at where should we map next and so forth. And so a very important activity, and it's still going on. Roughly about 1/3 of Missouri has been mapped in great detail. So this is William Smith's geologic map. And so what you see here, in fact, in this geologic map is that he actually noted the rock type there. He did not know what age those rocks were. In fact, he had a vague feeling for what those rocks were, but he didn't. Those rock units had not been named yet, in fact. And so it was somebody else who came up with the idea that we should name these rocks that have various fossils in them. And so, in fact, the guy who did that was Sedgwick, and then also Murchison. They were both, it was an English and a Scottish geologist, and they said, it was Sedgwick who first proposed the idea of a Cambrian time to separate the rocks that have abundant fossils from those that don't. And so we have Cambrian, we had Precambrian. And it was Murchison who came up with the idea of the Silurian, and together the two of them came up with the rocks in Devon. And they said these are Devonian age rocks because we have this certain group of fossils that we find in them. And so that is the geologic time scale then on the right-hand side here. So in the geologic time scale, we go from Precambrian, which would be the Archean and the Proterozoic down here at the bottom. That's lumped together very commonly and called the Precambrian. And then above that, we have Paleozoic, rocks that have fossils in them from ancient times. So the Paleozoic, ancient life. And then above that, of course, we have the Mesozoic. And so the Mesozoic is it's the time of dinosaurs. It's middle life is what that means. So that's the Triassic, Jurassic, and Cretaceous. In the Paleozoic, we break it into what we call time periods or systems. The systems are the rocks, and the time periods are called periods. So Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, that's what we see in North America. In Britain, they would call the Mississippian and the Pennsylvanian together. They lump them together and call it the Carboniferous. And then lastly, we have modern life. And so modern life is up here at the top. And if you recall, we were looking at Cretaceous age rocks. Okay, so that's the end of the Mesozoic there, overlain by Oligocene rocks. And so there's, it's 33.9. Okay, so I stand corrected on that. I teach this all the time, but I tell you, some of the numbers leak to ground for me. We have the Paleocene, the Eocene, the Oligocene, the Miocene, the Pliocene, the Pleistocene, the Holocene there. Now, those are what we refer to as epochs. But you lump those together, in fact, and so if you took the bottom four, they call that the Paleogene, and so the Paleogene is a time period. It's another period, if you will, that would follow the Cretaceous, the bottom four epochs there that are on the right-hand side of this image. On the top three, those are called the Neogene, and so the Neogene are the Pliocene, the Pleistocene, and the Holocene. I'm going to have to check on this because I think the Miocene is still part of the Paleogene, but I'll check on that. So that is the way that the fossils stack up, and that gave us what we call the relative time scale, if you will. It's the geologic time scale. And so if the Cambrian was proposed in 1835, after the map had already been made for much of Britain, Sedgwick studied the rocks, other people came along, and they began to name these periods. And so it was something that was important to be able to map those areas out and to see where the rocks actually cropped out. This is an image from Ray Troll, and he did a book with Johnson here, and so together they published these sort of cartoon versions of the geologic time scale here. And it shows you what some of the fossils are here as well. So in the very earliest, in the Cambrian, he's got trilobites down there. And by the time you get into Silurian, you're getting sea scorpions and things like that. And by the time you get into Devonian time, you're getting tree fossils and things like that. And you finally wind up at the very youngest up here at the top, and you'll get things like Ice Age animals. And so that ties right back into the book, Other Lands, because he starts out in the Pleistocene, in fact. And so in the Pleistocene, he talks about the megafaunas that were roaming, the horses and the tigers and so forth, that were the big cats anyway, that were roaming the Arctic regions of Beringia. Okay, so that is a geologic time scale. What it doesn't tell you is that there's a clock attached to that. Well, what's that clock? You can see the numbers over here on the right-hand side. You cannot look at a rock and tell what age it is necessarily unless you find fossils in it, right? So fossils are the clue as to what the relative age is, but it doesn't tell us like it's 542 or 395 or those numbers. Where do those numbers come from? Well, that's where we're going to have to venture into the other type of age dating, and that's called absolute age dating. And that relies mostly on radioactive elements. And so radioactive elements that are incorporated into sedimentary rocks or igneous rocks, we can date those things with the content of uranium or the content of lead in those rocks, uranium-238 or uranium-235. And so that becomes an important aspect of this. But that didn't even happen until the 1950s. So it was kind of a revolution when it did happen. There were older attempts at doing this with rubidium and strontium and a few other sorts of age dating techniques, but they weren't nearly as accurate. Today, when age dates, if you look on the age dates on the right-hand side of this illustration here, it's 0.5. That's 500,000. If you can date something to like 0.1 or 0.2 million years, that's pretty accurate. And that was a revolution that revolution happened in the 1980s and 1990s, and people began to fill in. So the unusual thing about this, when we had these absolute age dates, that people began to go out and collect the right rocks and use the techniques that were right up to, the latest techniques. They didn't find any discrepancies between the relative age dates and the absolute age dates. They all stacked in one after another. And so that was pretty important. It was a test of, the geology that people have been doing for 200 years almost, 150 years. And so because of that, we have this diagram today. Now this is from the Geological Society of America. There are two competing time scales. The other one is from the IUGS. It's the International Union of Geological Sciences. It's more of an international sort of group. But for North America, we mostly use the GSA time scale. For instance, we use Mississippian and Pennsylvanian, whereas Europeans would not. They use Carboniferous, even though it's shown on here, in fact. But you can look at this. Now, this thing is not to scale. I have to point that out. 90% of geologic time, by the way. So, the way to read this thing, start in the lower right-hand corner, and that's the oldest rocks on Earth. That's 4.5 billion years old at the very bottom down there. And you go up that column all the way to the top, and you're at 542 million years. But it is not scaled very appropriately because you couldn't fit all the names and everything in there properly, okay? And so that's 90% of geologic time just on that right-hand column. That's our Precambrian, like we were talking about. If we look at the Paleozoic, that's the second column over from the right. And you look at the Cambrian down here at the bottom. You see the same succession, Cambrian, Ordovician, Silurian. It's a way that we talk in geology. It gives us a language in order to communicate. These are the rocks that I'm looking at. These are the things that I find there. Whether you're looking at isotopic signatures for certain rocks or certain depositional environments for certain times through history. Remember, we study time. That's the Paleozoic. Okay, so the metal time, right? So Mesozoic is that third column over from the right or the second from the left. And the Mesozoic here, in fact, has the Triassic, Jurassic. You're familiar with Jurassic from all the movies and everything. And then the Cretaceous at the end. Well, the dinosaurs died out at the very end of the Cretaceous. And, in fact, most of life died out at the very end of the Paleozoic. That's the biggest extinction on Earth at the end of the Permian. So these extinctions, its life really plays into how we even view geologic time. That was 252 million years. And if you look at the end of the Cretaceous, that's 66.5 million years there. And then on the left-hand side, that's the Cenozoic. And we're still in it, right? This is people have even proposed that because man has been so disruptive to the natural environment that we should have a new time period added to this. It's been proposed. It's not been accepted yet, but it probably will be. it's going to be called the Anthropocene. And so the Anthropocene will be the end of time as we know it, at least for humans. And so the Anthropocene are the things that were affected by humans. But here you can see the Neogene. The Neogene actually starts in the Miocene here. My mistake there. So the Miocene, the Pliocene, and then the Quaternary at the very end up there are included those are the three time periods. So the Neogene, the Paleogene, the Neogene, and the Quaternary are the time periods within the Cenozoic here. And the Quaternary is the Pleistocene and Holocene. So here you have how we divide up, how we slice up geologic time, and how we communicate it with others, either in written language or in talks and things like that. So that, and you'll also see on here actually the absolute age dates listed along the right-hand column on each one of these. And there's actually a scale on the left-hand side as well, but most of these, if you compare the scales from the first column to the second column, third column, fourth column, they're not the same scale, in fact. So the last one is 66.5 million years in duration. The Mesozoic is 252 to 66.5. So, yeah, that's a geologic time scale. Anyway, I hope you enjoyed this, and we will go on with the absolute age dating next in order to describe how the right-hand column was placed into the geologic time scale. Once we get time out of the way, we're going to talk a little bit about plate tectonics next and how the Earth works, and then we'll get into fossils and the actual organisms that lived in the geologic past. Anyway, thanks for your attention, and we'll move on with the next topics here. Anyway, I'll talk to you soon. Thanks for your help.